2. Okay, so if I have a weight vector and I get an example, and that's my continuous differentiable loss function, at each time step we observe xt, make a prediction, incur a loss based on the true
y hat, right?
What?
Is this y minus y hat?
Yes. Yeah. Right?
No, because we're looking at a specific training.
So I'm just saying for this particular example.
Oh, yeah, okay.
So the subscript's t because we're saying we're getting them in time.
Yeah.
Update the weight vector accordingly. Write down the weight update rule using stochastic gradient set in terms of the weight vector, the loss function, and the learning rate. So w t plus 1 equals wt minus learning rate partial differential of the loss w x. And this is defined, it's just, d over d. So it's just the SGD update. Okay, 3. So for learning a decision tree with noise-free data, and start with the wrong attribute for the root node, are we still able to learn a tree that's consistent with the training data?
Yes, as long as we don't overfit.
Well, no. Yeah, the answer is you can, but you might overfit.
Right. Okay. But yeah.
It may not be the truth. It'll be consistent though.
Right. It'll just be.
It might. I mean, it might look stupid. It might look like, right, something's.
It's like you're essentially memorizing the data, as you said.
But I mean, you're still just learning a consistent tree has nothing to do with performance. I'm just saying it's consistent with the training data. The exact answer I wrote down here is I said yes, decision trees learn DNF, so it can learn any logical form. I will post these notes. The ordering of splits determines the size of the tree. Our expectation is that it'll generalize worse if you split out the wrong. Question you said?
Yes, this is actually a logistics question. So, number 2, you asked us to essentially give you an equation, but say, you didn't mention how you're going to give us all the equations we need to solve the problem. So, say there's another problem that asks about gradient descent, and that was
there.
Well, it's right there. It says the loss function is
so if it was given,
WX.
If it was given, then well, to be
I
honest,
just want to take the problem. I wrote my equation down. Like, is that all you're asking?
Yeah, that's all I was asking in this case.
Okay.
To be honest, these are not really practice midterm questions. They're just kind of good questions that are related to questions on the midterm.
But say we were to use the equation
from another part.
Yeah, and you're going to be giving one to us, right?
Yeah, I'll give you. No, and actually, I'd probably give you this exact equation. And frankly, if I gave you the equation, I wouldn't say it's the end. If you could just recognize the equation, I mean, in the things you'll know, I'll have this equation in there. So if you just wrote it down, that's fine. Yeah.
Let's also do there. I mean,
No, because you're subtracting the error.
Yeah, you're subtracting the error, so I'm defining this.
So you're trying to get closer to the really.
I'm defining it that way, but yeah, you could flip it and say that I mean, if you were clear about it,
yeah,
then you say that your error is the change in error.
Yeah.
You'd be fine.
you change also the other direction.
Okay.
Okay. Does everyone follow 3 here? Okay, 4. So the justification's good, but the question's actually not great. So the distribution of data is no will naive-based perform at least as well as all other classifiers. So the answer I wrote is if the data is conditionally independent, the naive base will perform as well as any other classifier on the training data. And I also said perform, it really should be on the training data. We really don't know anything about the testing data, frankly. And I'll add that to the thing. Because it could be that the testing data is not even from the same distribution and it violates our assumptions in that way. The reason this isn't a great way to state this, I was really trying to ask about conditional independence and perform at least as well as other classifiers. If you say, like I said, if If it's conditionally independent, then it will do as well. If it's not conditionally independent, then
We don't.
it doesn't really, you don't know anything.
We
So
don't. We have no.
it's either yes or no. It's really, I don't know.
Yeah.
Didn't we do it in
And
the?
that's a poorly written question.
In the last lecture,
Yeah, I talked about this, but it's just that the problem is that I'm saying if the distribution's known, okay, if it's conditionally independent, then this will perform as well as anything else. If it's not conditionally independent, then like all bets are off. I don't know, any answer you put down is correct. So, well, like effectively I would have to throw out the question. If somebody said, yeah, if somebody was to say, you know,
So you put
oh,
not
it's
the
not, if it's not conditionally independent, then everything's great. It doesn't, I know nothing. So will naive base perform any better than any linear classifier? It's basically the same answer as A. The key is if it's not conditionally independent, it will almost certainly do worse. If it's not conditionally independent in this case, it may still do better than lots of other classifiers. It's not really clear. You just know nothing. So it's a bad question. The second one makes a little more sense. That if the distribution is known and you know it depends if your data is linear, it depends if it's conditionally independent, and it probably will do worse if it's violated. Yeah. Anyway, yeah, you get the idea. It's not a great question. Okay, so assume we have two Bernoulli distributed variables that are independent. Is the negation of x and y also independent?
Wait.
Any predictions or knowledge?
we know that not x is x by the probability of x minus 1, right?
You know that. So what you know, so really what you should do here is marginalize out y. So yeah, I mean the answer is yes. So something we know, just based on probability, that p of y, and actually if you draw a picture it's really obvious. I haven't decided what I would give in terms of credit for a picture, but it's abundantly clear in a picture. So since you know this, then you know that p of not x and y equals p of y minus p of. Is this serious like this stinkiest? All right, so equals p of y, and we know they're independent, so this is px, py. And you can py 1 minus p of x. P of y, p of not x. And
Yeah, that's it.
yeah.
But Kevin, won't this be true for any distribution of x and any distribution of y at first?
This is true for any, right?
Yeah,
the only
everything
thing I
that
had to
follows-
use, the only thing I had to use was this because it's just that it's negated,
Oh,
right? So I can't negate a multinomial or negate a Gaussian.
oh, okay, yeah.
Yeah. So that's the only important thing is just that this will, when I move the screen, it'll make no sense. Okay, 6. Another case of me thinking the problem was easy until I did the solution. Yeah, let me mute this. Okay, I guess I'll give people a second to read it first. If you haven't read it yet.
I didn't see no whiteboard.
Yeah. So the hint I guess I should have put down is probably to use Bayes' rule, obviously. But it's a little trickier than I thought. So. And it's a little too hard for the midterm. But as I said, interviewers love this crap, so it doesn't hurt to take it. So what I did here is I define a variable, s, and s equals c1 plus c2. Or if you prefer, S equals this this DNF, C1 equals 0, and C2 equals 1. And I know that they're not technically equivalent, but they are for the purposes of this problem. All right. And then what we basically want is that P of C1 equals 0, C2 equals 1, conditioned on S equals 1. And now I'll do the Bayes rule, PS equals 1, conditioned on C1 equals 0, C2 equals 1. And I have this conditional, I have the dependence is only one way, right? So it's that coin 2 equals 1, given coin 1 equals 0, P coin 1 equals 0, over C1, C2. And I know that there's a constraint here that I'm only concerned with the case where S equals 1, but we'll get there. S, C1, C2, C1, over PC1. Yeah, I'm restricting, okay, I actually wrote it, that's nice. Restricting to S equals 1. So what I end up with is I only have to consider the two cases in the denominator of, I'm conditioning on this, so I only have to consider the 1001 case. So what I have up here, so probability S equals 1 given this is 1. So this is 1. Probability of C2 equals 1 given C1 equals 0 is I hope 0.5. Probability C1 equals 0 is 0.5. And this is one of the cases that I care about. And then I care about this case where C1 equals 1 and C2 equals 0. And the probability of that is a 1 if it's reversed, this is still probability 1 times 0.3 times 0.5 because this is fair, and C of 2 equals 0, C2 equals 0 given C1 equals 1 is 0.3, 1 minus 0.7, which equals 0.5 over 0.8, which equals 5/8. Yeah.
So we have two values for C2 and C1, so shouldn't there be 4 terms in the denominator?
Yes, yes. So there's 4 terms in the denominator, but I know that this, I only have to consider what the cases where S1 equals 1, or where S equals 1.
Yeah, but like still C1 and C2 will still be 0, 1, 0, 1.
Yeah, sure. There are 4 cases that exist, but I can restrict myself to those cases because I'm conditioning on. I'm conditioning on that I said to myself that I said S equals 1,
Yeah,
right?
even on S equals 1, I still have 4 cases. C1 can be 0, 1, C2 can be 0, 1, interchangeable. I can get heads on one and the tails on another. I can get heads and heads, then I get tails and heads.
No, but heads and heads, then heads and
We have
That's
to
not
have,
what we
one
observe.
has to be,
Okay.
one
Yeah,
has to
right,
be heads, one
Okay.
has to be.
it has to be an XOR.
Okay,
Right.
that made sense.
Yeah. No. Totally reasonable.
So why is the numerator 1 times 0.5 times 0.5?
Yeah, because the probability that S is equal to 1, given that there's exactly one head, that is one tails and one head, is going to be true.
Yeah. So that one makes sense. These two were given in the problem. Yeah, not a great problem to be honest, but something like this is reasonable.
This is the second time we've seen it, everyone.
Alright. Yeah. Okay. So assume that, assume that we estimate the parameters in 9 Bayes, write down the equations to describe how to compute the density. So just chain rule. that I said for naive Bayes. And so for this particular case, xy given z. Oh, Jesus, I'm right now in part 8, problem 8. Okay, 7's even easier. Sorry, I was wondering what I was doing there. This is just obviously y prime and y. I equals 1 to b of xi given y prime. You can put the py here if you want, b of y prime.
Wait, what's that?
Sorry, I'll write it again. I put py over here. It doesn't matter, but people sometimes like their variables nested more friendly. And 8, I apparently wrote the solution down because I didn't realize it was only one line. All right, so the question for 8, I guess I'll bring it up. So this would definitely be a fair question. I would put the same one on your exam, but here, let's do it that way. So show that p of x, yeah, I don't know why. So this is the chain rule, just in general. And I'm saying show p of x, y given z equals p of x given z, y given z, assuming we know that. And all it is that you just have to break this by the chain rule, and you're done. So, I mean, this is the only step.
So our x1 x2 x7 like features